Okay, AP Chemistry kids, this is an example problem that I wanted to go over with you guys because it is part of some of your homework problems. And this is pertaining to adding a strong acid to a buffer solution and then calculating the pH after that strong acid. If you're checking, this is number 21, and the example that I'm doing is D, as in David. So let's go, this is for chapter 15, so let's kind of get right to it. It's asking you to calculate the pH after, and I know this part is weird, so you're adding moles of HCl, but you're not really changing the volume. You're adding 0.020 moles of HCl. Remember, HCl is a strong acid, so that's going to completely dissociate it. And you're adding this to the 1 liter of the buffer solution that's made from a 0.1 molar HC3H5O2 and 0.1 molar NaC3H5O2. And I'm giving you the Ka value for that weak acid as well. So now the thing to consider is that, so now that conjugate base, so you got to figure out what is going to be reacting with that HCl, because this is going to dissociate and give you H plus and Cl minus, and of course the chloride ion isn't going to have any acid-base properties. It's going to be inert, but this H plus is going to want to react with which species? Is it going to want to react with the acid or with the conjugate base, which is right there? And it is indeed, that's going to react with that conjugate base. So the reaction becomes C3H5O2 minus will react with the H plus to absorb those H pluses from the acid. And what you're going to make then is the weak acid HC3H5O2. And that's going to stay intact. Not very much of this is going to dissociate. So what's interesting now is that we have to do a stoichiometry before we were to do Rice tables or any of that kind of thing. So considering the stoich, so I'm going to kind of label this as stoichiometry as far as what is happening. If we look at before the reaction, so if I'm writing out here before the reaction, I'm just going to use this right here as my equation. So let's say we have a liter of this. So I'm going to type in or print in 1 liter, and we've got the molarity, which we know is 0.10 molar. And I got that from right up here. Okay, so that's going to give me 0.10 moles. The acid, we know from this problem, is 0.02. So there's 0.02 moles of H plus. So I kind of have that under the H plus part. Okay, and then what would be the concentration of that weak acid before the reaction started? So this also, we had 1 liter and we had 0.1 molar of this as well. So this is 0.10 moles. Now what's going to happen after the reaction? So what's going to happen is, let me just change the color here a little bit. This is going to get used up. This 0.02 moles of the acid is going to get used up. And so what we're going to have is 0.10 moles. That's the original concentration of the conjugate base. And that is going to react with this acid to produce more of this. But to consider how much of this is going to be left, it would be 0.10 moles minus the 0.02 moles. Okay, and so that's going to give me a total of 0.080 moles. So that's how much of the C3H5O2 will be left. The H is going to have nothing left. It is the limiting reactant, so it's going to get all consumed. How much of the HC3H5O2 will be left? Well, let's see. We're adding H to this to make this, so the reaction is going to be making this. And so this is going to be 0.10 moles, and we are going to add 0.02 moles onto this side of the reaction. So that's going to give me a total of 0.12 moles of the acid. So now here I could choose one of two things. I could do Rice tables, or I could do Henderson-Hasselbalch. I'm going to choose to do Henderson-Hasselbalch because I think it's a little bit easier, but you certainly could do this through Rice tables. But this is an example of where you have to do the stoichiometry first, and then you do the equilibrium problem, or you do the Rice tables, or you do the Henderson-Hasselbalch problem. I'm going to do Henderson-Hasselbalch just because it's a little bit easier. But what I do need to know is I need to know my concentrations. So after equilibrium, or after the reaction, I should say, not equilibrium, but after the reaction, once I'm completely have done the reaction, my concentration of C3H5O2 minus is going to be 0.08 moles. Now remember, I want concentration, so that's going to be over 1 liter, which is going to give me 0.080 molar, and my concentration of the acid is going to be 0.12 moles over that 1 liter. And this is an example where I have 1 liter. Remember, you might not always have 1 liter, so you make sure you're keeping track of your moles and your molarity, because they are different. Let's see, this becomes 0.12 molar. All right. So now I can say that the pH is equal to the pKa plus the log of the base, which is this, over the acid. So the base is 0.08, and the acid is 0.12. And I should plug in my pKa. Where am I going to get the pKa from? Oh yeah, that's right. I can say that the pKa is equal to the negative log of the Ka value, which was given to me as 1.3 times 10 to the negative 5. So when I do that math, I come up with 4.886. And I'm just adding a few more significant digits. I'm going to round at the end. This becomes 4.886. And now when I simplify this term, the log of 0.08 over 0.12, I end up with a negative 0.176. And here in my pH becomes 4.71. So that is how the pH is changed after the addition of the acid. I hope this helps.